Good morning, everyone. I hope you enjoyed the hospitality of the CyCon yesterday night, and you were not crazy enough to drive to Riga for an Iron Maiden concert and get back. So with this, those who were actually at the CyCon dinner, you already experienced part of the session that we're going to tackle. So this is bringing a historical events into the virtual reality, or addressing the digital twin technology in the current era. So with this, we keep moving, and this session is Virtualized Environment and the Available Complexity. With me, I have the panelists, Joe, Sid, and Aybars, who will going to introduce their topics and explain their field of research. Before we start, there are a few house rules. Each presenter has 20 minutes, and after which we're going to have 10 minutes of Q&A. Within the Q&A, everyone here present is encouraged to ask questions, as well the other panelists are encouraged to engage in the discussion with the rest. Without further ado, let's keep moving. Joe is going to be the first one, and he is a PhD student at the University of Plymouth, and his work is focused on exploring the digital twin technology towards increasing Dockyard's efficiency.
Thank you very much.
The crowd is yours.
So to begin with, I'm going to look at the background of the site that I'm working on, which is HMNB Devonport. That's Her Majesty's Naval Base, Devonport, which is in Plymouth, which is in the southwest of England. It's the largest naval base in Western Europe. It has over 650 acres of land and 4 miles of waterfront, and employs over 2,500 service personnel and civilians. It's the largest energy consumer in the area, and possibly the entirety of the city, and it's one of 3 Royal Navy dockyards in the UK. One of the main challenges for digitization for this site is that it was built in the 17th century, which means much of the infrastructure has not been designed for digitization. It is home to the Royal Navy's amphibious ships, survey ships, and half of her frigates. It has 15 dry docks, 25 tidal basins, and 5 basins for maintenance of those vessels. And also it has training facilities for flag officers sea training and also submarine training. Barracks, that includes medical dental facilities for those living on site, and also recreational facilities and accommodation. So it's quite a large, complex site to try and to optimize. So digital twin, this is what I'm researching at the moment. And my understanding of a digital twin is that it's a virtual representation of a physical entity. Now, if you ask lots of people what a digital twin is, you'll probably get lots of different answers. So to name a few, IBM say that it accurately reflects a physical object. NVIDIA says it has to be a true-to-reality simulation of physics and materials, which has to be continuously updated. And then Forbes has a similar description to what I have given. But they all have the underlying definition of that it is a virtual representation of a physical entity. Now, what are we going to be doing? We're going to be modeling the entirety of the dockyard as a digital twin. And that is going to be, for a number of purposes, to be able to understand what the current limitations of the dockyard is and how they can be improved. Why are we doing it? Well, that's twofold. First of all, the Royal Navy wants to know what they can do better. So we've got an old dockyard that can be improved. We know it can be improved. By building a digital twin, we'll be able to find out specific ways in which that can happen. And secondly, due to the scale of the site and the complexity of the site, academically it's an interesting topic because we're looking at a digital twin of a large area with a completely different goal to other twins. Because as the Royal Navy dockyard is military as opposed to commercial, the goals of the site are also completely different. We're not looking at trying to make as much money as possible. We're trying to make sure that our military assets are available as often as we can. So what do we hope to achieve? By the end of this project, we hope to have a proof of concept for how digital twins can benefit a Royal Navy dockyard, which should then provide results as to how much the output, the results of the optimization of that twin, if implemented, can actually save the dockyard either money, reduce carbon emissions, or improve the availability of vessels. So the digital twin specifically has 3 key domains. First of all is the infrastructure, which looks at the buildings, roads and pathways, and critical port infrastructure on the site. All of that needs to be modeled. Then we have a utilities domain, which looks at communications, energy, and water. And then the operational domain, which is asset tracking, people and teams, and workload. So each of those domains contain a number of layers, as I've just talked through, and those layers will all be individual models. However, what makes this a digital twin is that all of those separate models will be based upon data from other layers. So it will all be interconnected. So make a change in one layer, that change, the effects of that change will be visible in other layers. So all of that will be modeled together to then give accurate results. So here's an example of how this could be used. If we simulate a power cut, that will be on the power layer of the utilities domain. That will then be visible on the infrastructure domain in the buildings layer. So one building may lose power. Now, one building, that could have a few teams working within that. That would then identify within the twin which teams have lost their ability to do what they need to do on site. That will show the impact of that power cut. Additionally, the people within that building may be able to work elsewhere. However, there may be critical network infrastructure, for example, an active network switch in that building. If that goes offline, then the communications layer will show you where people on site may lose connectivity. And then again, other people may not be able to do their day job. So you'll be able to simulate outages around the site from maybe one small outage. So the stages of development start from modeling. So that's making sure that all of the models we create are accurate to the site with the right level of abstraction of data. Then we need to analyze the site in its current state, looking at what the potential limitations are, and also looking at where we can improve. And then finally, we have optimization, which is finding solutions to those problems, and also problems that maybe individual people on the site have themselves. They'll be able to input those problems to find a solution through optimization. So modeling, what are the challenges of modeling? Well, first, we have the data collection. Being a 17th century site, some of the data may be difficult to find or difficult to gather. So that is a really key problem that needs to be overcome early on to make sure we have data. So I've started with the communications layer because that is a layer that has as much data as I need at the moment. But as I go forward, I'll need to find ways to collect data that may not be as easy to gather. Then we need to make sure that the data is accurate and relevant, but also that the model that's created is accurate and relevant to the site. There is a really key point with digital twins that if the model isn't accurate, the results you get out will also effectively be invalid because it's not going to show you what the true state of things are. So from this stage on its own, it will be beneficial to users on the naval base because they will have access to visualization of the current state of all of those layers. So if you're working in one key area, you'll be able to use the digital twin to find a visualized way of representing that data so they can complete their day-to-day job slightly easier than current. Next is analysis. So analysis is looking at identifying vulnerabilities, specifically through single points of failure. That's the first area that I'm looking at for identifying vulnerabilities. So that is looking at a single point on the site that if that point was removed, has the greatest impact over the site. So there'll be so many points within the site that if you remove will have an effect, almost all of them, but which one has the greatest effect will be found out through analysis. And that will look at each layer and also look at the impact across other layers. So across the priorities of the naval base, which are primarily to improve availability of vessels, but then also we do want to reduce our expenditure and reduce our carbon emissions, we will have a fitness score through the analysis for each of those topics. Initially, that will just be an arbitrary number, but every change that is made, either through optimization or through a manual change, those three fitness areas will be scored, so then we can assess as to whether the solution is better or worse for those. We only want to pursue solutions which have an improvement on the priority for that work. So the user with this stage will be able to make minor changes to the data, monitor the impact on the fitness scores, and the purpose of that would be to aid decision-making. If it's better, then they can go with that. But then finally, we have optimization, which uses genetic programming. So using single objective optimization, just to solve the problem. You've got a key problem that needs to be solved, regardless of anything else. we can run an optimization algorithm to find the best solution for that problem, which is really good. However, that may have very expensive costs for other priorities of the naval base. So that is why the digital twin will also look into multi-objective optimization, to then look at all of those priorities together, where the main one is to solve the problem we're trying to solve, but also if we can do that in a way that reduces environmental impact and reduces the total expenditure of the site, then that is a bonus as well. And that will produce a selection of possible solutions, so the decision makers can consider everything, because sometimes it is worthwhile to spend a bit more or have a bit more carbon emissions if the end result is going to be better. But this should give them all of the data they should need to be able to make those decisions best for the decision that he's making. So where am I now within the development? I'm right at the beginning. So I've modeled the communications layer of the site, and that is where I'm at the moment. Starting the analysis stage next, I have lots more data to collect to be able to model the remainder of the site to make it a digital twin. At its current state, it is just a computer model. It's not a digital twin yet, but that is where I'm going to be able to run optimization algorithms on the site. Other challenges I have being a military site is that all of the data that I'm collecting for the site is confidential and can't be published. So that is a big drawback from my PhD research, is that I can't publish what I'm doing. So to go around that, I've tried to create artificial data that represents something similar to the site. However, that has proved, doing that autonomously has proved quite difficult, because automated data to design a network looks nothing like a network. So what I've done is I've created a set of data which is much smaller than the Dockyard, which allows it to look almost like a network, which has worked. I do have that data and I can publish that data. However, it doesn't accurately reflect a real-life scenario. So that is not ideal for this type of research. So I've been speaking around with other ports, and I found a third party that is happy to provide me all of the data that they have and allow me to publish all the data on their port. That is a commercial port in the UK. They've asked to remain anonymous at this point, but that will allow me to go forward publishing all of the data from that port while designing the same digital twin for the Royal Navy, which remains confidential. So looking at what I've done so far, the image on the screen shows you a diagram of that network. This is artificial data. It does not reflect a real site. Each of the points is a node. That would be a building, because at the moment the communications layer is building specific, and each point, the size of the point, is how many neighbors come off that, how many buildings that is connected to. It's not geographic, so there's no coordinates there. It's just based on trying to make the image with as few cross lines as possible. Interacting with that, if you go to one of the nodes, you can see all of the neighbors that are connected. So for the view of an individual user trying to interact with their day-to-day job, rather than trawling through a long Excel spreadsheet to try and find which nodes are connected to which buildings, this would make it a lot more graphic, and being able to overlay this with a physical satellite representation of the site, which would then move the diagram to the correct coordinates, would then allow much easier interaction from those end users. And being able to see the neighbors, that's not all we need, because often there are many connections going between the same two buildings. If you look at the edge, you can see the actual ID, which is affiliated to that final that connection, which will massively help the end users using that. So that's very similar with the other utilities layers. So with power and water, they will be designed in a very similar way. However, looking back to the different layers that we'll be modeling, there'll be certain things that won't be able to be modeled in this way. So buildings will be derived from the satellite imagery. All the utilities will be derived in this way. But then looking at the right-hand side, which was operational, that is something that's going to be very unique for each layer. So first of all, we have asset tracking, which is arguably one of the easiest ways or best ways that we can actually derive results from this digital twin, because that will track all of our infrastructure, and at the end level, it would be everything from sort of small items of use all the way up to all the cranes and port infrastructure. Asset tracking will monitor everything that item is doing. It will look at when the engine's running, when it's actually in operation. The statistical analysis, all of that data should identify where we're going wrong. So if an item is hired for 2 weeks, but it's only used for 3 of those days, so therefore an external item has to be hired in, and that is only going to be, that's also hired in for 2 weeks, but it's only used for a different set of days. That is a waste of time. We could just use that same crane, or it could potentially be that another job has to be put on hold because that item is being used elsewhere, it's hired, but it's not actually in use. So being able to look at that data will give us information as to what is being used and how we can improve things. Then looking at people in teams, that's going to look specifically at where people need to be working. So some jobs, office-based jobs, can be done across the site or potentially even remotely. So they will be modelled, but they will have a clause that they can work elsewhere. So that is not a vital failure if they can't work in their building. However, other work has to be done in that location. So if one of those buildings go down, that will then identify that work cannot be taken and it will not be going forward. So I'm afraid I've finished a couple of minutes early. I hope that's not a problem. But I'd be happy to take any questions if you have them.
Thank you. Take your seat, and then we're going to dive into the discussion session. Now, when I read Joe's paper initially, I felt he's trying to recreate the 90s game Transport Tycoon. We all loved playing back then. However, the level of complexity that you're trying to bring in is fascinating. Currently, at this stage, you're more playing with the digital doppelganger versus digital twin, and you are trying to facilitate the decision-making process to make the dockyard working more efficient. Now, if we look at the layers, you're currently working with the implementation of the communication layer. A communication layer, what components have you already considered for implementation, and how's it been going with this one?
So the communication layer is looking specifically at where the buildings are, how they're interconnected. So it's looking at their neighbours to create that map. It does have other data included, which is sort of how many cables and connections there are within each cable, and how many cables are going in the same direction. That's data that I can use in the future. But the implementation of that in the model is it's very much an analysis of how nodes are connected together, and it's just a plain script which I've written myself. It's nothing, no framework for that.
Right, but when you're going to carry on with further implementation of the communication layer and also other layers, how granular do you think you're going? If you're saying that you're going for the buildings, first the physical layer, buildings, if you're going to target physics, rain, everything that can actually have a significant impact on the dockyard functionality. If it's icy, can the employees get to their work? Can the cars drive within the campus? And if you're looking at the data connectivity layer, would you go and try to emulate some network protocols that are there as well, or that is totally out of the decision-making process?
It's definitely not out of the decision-making process. The idea of the digital twin that finally, if they implement this on the site, as much as can be modelled would be modelled. But within the scope of my project, what I've done for the communications layer at the moment, I'm going to leave that as it is, so that I can add as much more into the total digital twin, which will then allow me to model everything as a whole, which will allow me to get the results, to monitor the impact before I go back and add layers of abstraction.
I understand. I would like to take also the questions from the audience. I know it's early morning, but and the first bird is Gabor.
And I got Mike. So a question: how do you plan the model quality assessment or the model quality analysis if you are restricted in the source data?
So I'm within a team at the Dockyard at the moment, the CIS team, and so all of the information and data I get from the Dockyard, I get through that team. So I've got those points of contact. So any results I derive initially, I don't expect once I first model something for it to be fully accurate. So that is going to be an iterative approach with that team to work through the data that I get to monitor the effectiveness, and then I can tweak the model until I get something that they all think is relevant, and then I'll see if there's other industry specialists on the site that I can sort of do final checks with.
Oh, excellent. Thanks.
Thank you.
Following the Gabor's question, so are you going to collect also historic data? Meaning that, I mean, maybe you can still collect prehistoric data before your research, or you're going just to start at this point collecting the data related to how the dockyard operates. What's also the traffic intensity, how the operations work there, what's the network load, and so forth. How are you going to collect, and what are the methods that you're considering for the data collection? Because you need to have a decent model there.
Yeah, absolutely. So lots of the Dockyard as it currently stands collects lots of data as it is, but it doesn't do much with it at the moment. They're all kept separate. So I've got lots of contacts that I'm looking to exploit to collect that data and build into the model. The future of the digital twin would be to have that data collection automated through IoT sensors spread around the site, because that's always going to make it as accurate as it can be, having real-time data. But for the initial model, it will be based on static data as it is now. So in my current stage, any data I can get my hands on will go into the model. As and when I can get updated versions, then obviously I'll update. But at my initial stages of development, I just need to get as much data as I can together.
Any other panelists? Do you have a question? Sid, go ahead.
I have a question. So with the recent events which have happened in like the global shipyard industry and the docking industry, especially in the United States, and we have seen the impact of what can happen when a critical infrastructure like that gets choked. So how do you plan to extend this work or make it transferable enough to be applied to dockyards which do not conform to the model that you are focused on? How flexible will this twin be?
That's a really good question. Yeah. So I think because I'm in the unique position now that I'm developing the dockyard, the digital twin for the dockyard, but also for a commercial port, there is going to be inherent flexibility within that, because I want one singular model to be able to take in either data set. So it's going to be built in with the priorities for certain things that will relate to commercial and also military within the same model, because I don't want to have to develop two completely separate digital twins for the same project. So that flexibility that will be built in there will allow it to be transferable between certain things. However, it's all going to be specific to the maritime environment in this state. So it's going to be ports or dockyard.
Okay.
Right.
Thanks.
Right. One of the questions that we have is also, would this model be applicable also something beyond just the dockyards? Can you apply it to anything else? And if yes, what would be?
Yeah, absolutely. So the digital twin technology is absolutely applicable to almost anything. The model that I'm creating, the digital twin that I'm creating, is specifically for the naval base down at Devonport, but also my third-party port, so it's going to have a bit of flexibility built in there. But additionally, the technology that is based upon would absolutely be able to use for other sort of places of a similar scale. So an airport, for example, either military or commercial, would be another application for this technology.
Or you're going for a very complex issues here.
Mm-hmm.
We have a question, Luke.
Actually, I had several questions, but you asked many of them. So I'm left with only two. And the first one then is for you, Bibi. Did you really drive to Riga last night for a rock concert?
I did, yes.
There's a couple of people in this conference that are, I imagine them like Terminators, like machines that just keep going nonstop, and Bibi's one of them. Okay, so the question is for you, Joseph. Congratulations, great research. Are you going to publish this model? Are you going to make it available? Do you believe that other people can contribute to it to enrich it, the semantics of it?
Yeah, absolutely. So due to the model being the model specifically for the port, the third-party port, all of that, including the data, I plan to publish, obviously with their permission from the data and results side. I plan to publish everything and make the actual model, the code for the model, open source. I was speaking to someone at one of the events earlier this week, and they've offered me some access to one of their company's GitHub repositories for some modeling system. So I absolutely want to sort of return that back to the open source world.
And I promised to the panel that you're not going to be the only one in the hot seat here, dodging all the questions. So I have a question to the rest of the panelists as well. But I'll start with the Aybars, and the same question will go to Sid. And this is purely theoretical. You don't have to provide me already the working details. How would you tackle this issue if you would come up with an idea of virtualizing or recreating a digital twin for a naval dockyard or an airport? How would you approach this?
Actually, this is a difficult question for me. Why? Because I'm not interested in the shipyard. However, many of times I entered the shipyard because I was a seafarer. And during this period, I saw that one of the most important issue is the human factor. And you need to simulate also a human factor in the shipyard as well. And you can see that many incidents is caused by the human factor. And in the digital twin, maybe, you can also mention about the human factor.
Right. Thank you. Sid, do you have any take on this?
Yeah, I'll pick up from where Aybars left. So the human factor is one of the most interconnected and interdependent pieces of any complex system, like a shipyard. So modeling that, modeling how trade unions work, modeling how the shipyard labor unions work, that has a huge impact on how the load gets transferred through the ship, through the docks. So that would be definitely one thing which needs to be modeled. And the second thing is I would look at how much fidelity do I want to go into the twin with. So so a digital twin, when people say it's a digital twin, it's either referring to a digital model, which means it's approximating some part of that physical process, or it's a digital shadow, which means it's getting inputs from a physical actual operational system and then trying to model the future states, or it's a completely bidirectional digital twin, which talks to and from this physical process. So these are the three popular ways of differentiating between how accurate do people want to get with these technologies. So maybe we can start with a very simple approximation like game simulators or Shipyard Tycoon or something like that. That can be the first step. But as we move to much more real world use cases, you will need to have this to and fro communication between the twin and the physical ships.
Right, yeah. Thank you. And I think Joe already mentioned that he would like to extend this with the sensor technology. We have a question here from the audience, please.
Yes, hi, Veronique. I will not stand up. Yesterday night was a bit much. So question to the three of you, potentially rather to the two of you, is how would that look like if you would apply it to a mobile station, let's say? So speaking about satellites, how would you... What would be your way, let's say, what would be the best approaches to model the links with the satellite, let's say? And then speaking about security concerns, obviously you can use the digital twin probably quite well to do some pen testing, to do, to find out where security gaps would lie. So yeah, rather general question, what is your take on that? How could you best implement digital twin on a satellite?
Okay. We'll start with Aybars, please, if you have any take on this.
Of course. Yes, digital twin for example, autonomous ship. For the autonomous ship, the security, cybersecurity is one of the most important concerns. And for the digital twin, it is like a digital twin. And nowadays, there are some technology systems are developing. For example, VDES technology. And through the VDES technology, there are some encryptions will be possible, most probably. And of course, not only during the attack. After the attack, we should be cared by the researchers. This is another story, actually. I mean, cyber incident handling. And still ongoing process, actually. Now, as I remember, the third version of the GPS, for example, was started to be tested. And against some cyber attacks, like jamming or spoofing, will be more resilience. Well, probably for the digital twins, it will be also useful.
Right. Sid, I will save you because you will be our next speaker. But before you are in the hot seat, I wanted to ask a transition question to you, Joe. We're going to talk about the exercises, cyber exercises. Would you say and briefly, would you say that your model could be integrated in one way or another into the cyber exercises?
Well, I'm by no means an expert in cyber exercises, but I can see the use case for digital twin technology with those exercises, having a real-life asset or environment being modeled, and then having that model visualized for the white team. I can see the benefit there, and I definitely think with some editing, it would be useful.
Right, thank you. With this, you can start relaxing now and start preparing for the questions to the rest of the panelists. With this, I would like to welcome on the stage Sid. He's a researcher at the iTrust Center for Research in Cybersecurity at the Singapore University of Technology and Design. His work is focusing on cyber-physical systems and exercises related to those. The crowd is yours.
Sure. And I will answer that question about satellites in my talk because it's extremely related to everything that we'll go into with cyber physical systems. So as you can see on the slide, the theme of this conference and the theme of like living a long, healthy life is to keep moving. And the way people have represented that in the digital sphere is this cellular automaton, which is called the Conway's Game of Life. So it follows very simple rules. And those simple rules let it just glide through the cyberspace. And this, the reason I bring that up is because this became the hacker emblem for cypherpunks in the early 90s, which is where the whole field of cybersecurity began. And now we are at a state where hackers or problem solvers in general are not just people who are underground, but people like you and me who work with the governments every day and try to protect our countries. So with the spirit of hacking and problem solving, we'll start the talk, which is about the design of cyber-physical exercises. And I am a researcher at iTrust, as BB just described. And for more context, I've been advised by Professor Aditya Mathur since 2016, so that's the last 6 years of my life. And I've gotten the freedom to explore like the whole broad range of emerging technologies. And that's what we will get into in this particular talk. And that comes from like a background in different fields. So I've interned at the Indian Space Research Organization, designed things at the MIT Media Lab, worked with financial infrastructures at Goldman Sachs, and more importantly for this talk, 2 experiences with the Google Summer of Code, where I worked on simulating a Martian rover, like a Mars rover, and the human factors involved in communication with astronauts and rovers, as well as organizing Complexity Weekend, which is an event we do twice a year with the best applied complexity scientists across the world. This has really led me to think how to best think about cyber physical systems, which are a much more complex system than just cyber systems. So if you look at the book that you received with the CyCon package, you'll find our paper on page 347, but you do not need to read the paper to attend this talk. I assume no background, and yeah, it will be a very gentle introduction to everything. This has been repeated. This message has been repeated throughout this event, in which we started on the workshop day with a very relevant talk and preparation by members in CCDCOE. So this talk was about trust in cyber exercises and the future vision for NATO as they go forward. And this talk especially focused on the importance of cultural communication, the importance of interoperability between countries, the importance of collaboration over competition or co-opetition and concepts like that. So it was a really good look at that from both a strategy point of view. And then it was followed by another excellent talk, which some of you might have attended, by Dr. Max Meets. And that was an analysis of the lock shields exercise. And this paper is the first paper in the book that you received. So this is the role of military cyber exercises and a case study for lock shields. And this was particularly very exciting for me because this went into the history of locked shields and how exercises evolve. We just assume that people like Gabor and the team, they just come, gather around and organize an event like this. But the history that has gone into events like this predates like a decade back. So an exercise like Lock Shield started like soon after there were cyber attacks on Estonia in 2007. And the first event that was conducted was the Baltic Cyber Shield. And 2012 onwards, it's been called the Lock Shields. And we at Singapore have followed like a very similar path, which is very serendipitous because these two series of events happened independently. And now they are in a sort of interdependence with each other. So after doing and conducting all these exercises, there's one thing we have realized, that the role of cyber exercises in increasing our resilience is extremely clear, but it's certainly not enough. And I'll get into why. This is because traditional cybersecurity is no longer enough. You see on your screen that there's a whole range of attacks which are purely cyber attacks. Then there's a whole bunch of attacks which are purely physical attacks, which the world is very good at planning and strategizing and thinking about since the last century, or even the last 1,000+ years. Now we are at a space where cyber and physical are no longer like independent things. Our systems around us, like from the smartwatch that I'm wearing to the phones that you have in your hands, they are no longer just cyber or just physical. They are completely a new thing of their own. And when people say the real world, they usually mean the physical world, which is also no longer true. Most of our lives are spent in the digital world. Most of the decisions that countries take happen in the digital world, and any manipulation with that digital world has physical world consequences. So when I mention real world in the talk, I refer to the cyber physical and not just the physical. So you see some examples of cyber-physical systems. And just like the question you asked about satellites, they are also very cyber-physical systems. They have some capability to maneuver through space. They have sensors and actuators on board. They have network links which can be compromised or hacked. So anything from pacemakers, which people have in their hearts, which can be controlled by Bluetooth and can be hacked. And you can essentially like kill someone as a result if the pacemaker has an anomaly or if the pacemaker has been compromised by malicious actors. To like large-scale, country-scale water treatment systems. Everything is driven by these communications which happen between sensors, controllers, actuators, computers, and this has large consequences in the future. And this has been very clear in the attacks that we have seen in the last decade, and more so in the last couple of years with the Florida water treatment attack and the Colonial Pipeline attack. These attacks may have their origins in the cybersphere, but they had large consequences in the physical sphere. So this became very clear in 2016 when NATO recognized cyberspace as one of the domain of operations. And this is because we had the 4 domains of warfare: sea, space, air, and land. And then cyber was introduced by a lot of countries in that area. And then here you see like weaponized social media and cultural engagement. Now this is something where memes play a huge role, and things which we have seen play a huge impact in global elections as well as day-to-day dialogue. Now what happens is that cyber-physical warfare is the next step. So cyber-physical defense and cyber-physical exercises are obviously the next step for us to think about. And this is why it's important to frame or define this term first. So when the attack has its origin in the cyber domain, in the information domain, it's purely a cyber attack if the impact is also felt in the cyber domain. So this can be something like just getting someone's passwords or just messing with your friend and changing their password on their phone. But if the attack is purely in the physical domain and also has an impact in the physical domain, such as me just drilling a hole in a tank, in a water tank, that's a purely physical attack. Now, when we go to origin in the cyber domain and an impact in the physical domain, that's when it becomes a cyber-physical attack. So this can be me just blowing a satellite up in space or attacking a remote water plant sitting here in Estonia and causing a flood in my water testbed in Singapore. This is a cyber-physical attack. And this is the most popular style of attack that is going on today, which we are not yet prepared, but we have begun to think about. And lastly, there's this very underappreciated, underexplored area called the physical cyber attacks, which we won't get into, but it's important to mention. So these attacks can have their origin in the physical domain, like me just coming with a hammer and blowing the servers apart. So this has an impact in the cyber domain, that the disks might get damaged, my processors may not work as expected, or I cause like changes in the voltage, and that causes impact on the computer infrastructure of the entire facility. Or a very popular example is signal jamming. I can just jam the signals of like all the communication devices here, and that has an origin in the physical domain, but an impact on the cyber domain. So these are things which we can use to explore the whole range of cyber-physical attacks. So it's just important to explore what a cyber-physical system really is. And very simply, it's anything with a sensor, with an actuator, and with some controllers, which help to understand the physical world around us, and then manipulate that world based on the logic that we have just come up with. So that manipulation is decided by controllers or computers. So these can be very simple things like Arduino microprocessors, which kids use to program simple things, to like even very advanced things like controlling nuclear plants or water plants. So all of this is done by a supervisory controller, which takes in inputs from all these smaller controllers, and that's why it's called the supervisor. And popularly, it's known as the SCADA, or the Supervisory Control and Data Acquisition Unit. So the abbreviations in this field are SCADA, PLC, which is the Programmable Logic Controllers. These two are the only ones you need to be aware of for this talk. And the reason the attack surface, or the points of attack, increase is because each of these things exist both in the physical realm as well as the cybersphere. And all the small letters that you see here are points of attack. These can be some things like supply chain attacks, which start with anomalies in the microchips itself, which we may not be prepared for, right up to like man-in-the-middle attacks and all different sorts of network attacks. So these things, which can be at the scale of sensors or actuators, or at the broader scale of control devices or utility devices, these have broad consequences. And this is why it's important to understand the difference between information technology, IT, versus OT, operational technology, which is what industrial control systems and cyber-physical systems are all about. And this is why CCDCOE has been on top of this since the last many years. And most of you would have seen this if you have attended CR14 or the cyber ranges in Lock Shields anytime. What does it mean for all of you as people representing different countries? These are our critical infrastructures, and all of them are essentially controlled by these cyber-physical systems increasingly. To take an example closer to home, these are Singapore's critical information infrastructures. And to counter that, to protect these systems, there's a whole of society defense approach, which is called total defense. And digital defense was one of the categories which was added in the recent years. But since society is this interdependent, complex being between technology, economics, culture, and policy, it's important to essentially understand the interplay between all of these things and come up with strategies to protect cyber attacks and cyber-physical attacks. So this talk is mostly about keeping calm and cyber exercising and introducing that as like a cultural practice among all critical infrastructures and countries around the world. And the paper will go into like 6 years of cyber physical exercises, and the exercises included are these ones. So there's one exercise which we conduct every year at iTrust in Singapore, and that's called the Critical Infrastructure Security Showdown, or CISS. Then we take and transfer our learnings from Locked Shields, which is an exercise conducted by CCDCOE, and it's a blue team defensive exercise. And we have been taking part, we were in the Locked Shields 2020 planning events, and we have taken part in 2021 and 2022, which just concluded a couple months back, and Crosswords, in which we met BB for the first time, and that was like an eye-opening experience for training red teams. And the importance of these two exercises independently and as a whole was very enlightening for us. And also for the organizers of the exercise, because they introduced a water system, which is a special system for these exercises for the first time. So yeah, all of this was built on more theoretical foundations, which started in 2015, where we had the same like test beds open at a much larger scale in the future years. So that was called Sci-Fi Systems Week, or Special Systems, or Cyber Physical Systems Special Systems Week. So yeah, this is the TV wall of CCDCOE, which is used in lock shields and different exercises. And you see our human-machine interface, or 24 blue teams here, 24 countries, essentially, or teams of countries, trying to defend a water treatment system. And the reason they are trying to do this is because attackers usually think in terms of networks and graphs and the relationship that different components have. How is my tank connected to a wall? How is my network link connected to a satellite? How is my shipyard connected to like the human who will be driving and using the truck to transport the load? So defenders instead have been traditionally thinking in terms of lists. Can I install a firewall with a list of rules and try to protect this link, this link, this link? Whereas attackers will always think in terms of like networks and graphs, and they will always be one step ahead because they have like a different view of the entire system. So if we want to be good defenders, we have to think about how things are related. And we do that at iTrust with examples like this. So this is essentially any cyber-physical system. And the red devil emoji is essentially points of attack, which can be network attacks between links. And that's why it's important for us to monitor each of these points. So the broader thesis of that is we have to monitor all the attack points as a good defender, and then visualize these security and operations and safety conditions in a very accessible interface, not just for technical operators, but also strategists and policymakers. So this is what we have been doing at SWAT, which is Secure Water Treatment Testbed at iTrust. And we have a whole bunch of sensors, such as this flow meter, which measures the flow of water, and an actuator. And these things look like this when seen from a computer graphical user interface. And the reason these things look like something straight from the 90s is because there has been no major innovation in like design and user experience in this field. So what we have done is we have come up with like modifications to these HMIs, or human-machine interfaces, and added detectors and more technologies to make it more obvious for operators to understand if there's an anomaly or an attack going on. And we have been doing that not just for water treatment, but different test beds, such as water distribution, Internet of Things, and an electric power test bed. All of these which will be used in exercises and have been used. So this started with an event back in 2015 called the Sci-Fi Week, or the Secure Cyber Physical Systems Week. And we wrapped up last year with CISS 2021, where we collected 85 hours of data, which does not seem like a lot, but that was multiple red teams attacking throughout the week. And we had more than a terabyte of data in the form of packets collected, and 0.32 GB of operational technology data. And we have opened up these data sets for anyone to access once you request from the iTrust website. And the distribution for that has been something that you see on the screen. So it's a very balanced red teaming, blue teaming exercise with a few judges and technical staff from the green team. And Lock Shields has a very similar model, and it has been interesting to observe the similarities and differences between the way exercises can be conducted. And the reason we have such a balanced way of approaching this is because we want to capture all the aspects of the NIST framework, or the NIST framework, which essentially helps us describe the security posture of any critical infrastructure. So it's important to not just identify assets, but also protect them, detect against any anomalies or attacks, respond to these attacks, and then recover from these attacks to ensure that the security, safety, and service of your infrastructure, as well as the people and the operations, is preserved. So we do that with a whole bunch of technologies, which we won't get into in this paper, but you can definitely come to our booth after the talk to learn more about it. But the idea is that you need a holistic set of tools and technologies and procedures to essentially counter that, because attackers are getting smart at every step of this skill chain. So if some of you are familiar with the MITRE attack framework, this is an easier representation of that, which is like a very recent pyramid called the tactics, techniques, and procedures pyramid, which goes into increasing levels of detail, like what command was launched to what strategy did the attacker have more broadly. And this leads us into more of a purple teaming mindset, which is something that's inspired from both the red team as well as the blue teams, in which you act both as the blue team and the red team depending on what area needs more attention. And once you do all these things, once you understand the state of the system through not just attack but also defense, you lead to a more secure design. And this leads us into the MITRE playbook, in which you identify and hold an IPC or an initial planning conference, then a main planning conference, then you conduct the exercise through something like Partners Run in Lock Shields, and then the final exercise itself. For us, it has looked something like this. So if this is your first time conducting an exercise, you can read more about it in the paper. So it's steps which are mentioned here, such as communicate and coordinate, implement green team systems, implement IT and OT protocols, create a digital twin if you need to, provide a database, then design the human-machine interfaces, design and develop attacks for red teams, implement anomaly detection, and create test plans and update the code. So this has helped us understand the increased importance of these techniques, tactics, and procedures, not just across twins, the importance of digital twins, but also user experience, detectors, and the need for protectors or safety instrumentation systems. So you might have seen just 4 names on the paper, but none of this would be possible with an entire village of people who have supported us in this journey, including people here at CCDCOE. So yeah, thanks to all of you. And this all started in 2019 when CCDCOE also visited iTrust for one of our exercises before COVID. So this was CISS 2019. And it was a very proud moment for us when our blue team systems, the HMI, were represented in Lock Shields for the first time. And one last thing before I wrap up the talk, CISS 22 is happening later this year. And this will be the first time in which we'll have 3 systems, not just one, but 3 systems interconnected for red teams and blue teams to play against. So yeah, that's the talk. If you want to know more about the work at iTrust or me, you can just take a picture of that and reach out, or talk to us at the booth outside or after the talk. That's right.
Thank you, Sid. You got a very condensed and archived version of the information. He has a lot of things to tell. So make sure you visit his booth and talk to him, and also the rest of the iTrust crowd. When looking at the crowd during your presentation, I've been on the other side as well. This is just Gabor invited me to sit in this chair, but I saw a lot of people taking pictures of your slides, meaning that they do have some importance in there. So, although the water is a common theme in this session, in this panel, although you might not know about it, we have shipyards, we have water purification distribution systems, and Aybars will talk about the water as well. However, I want to just slightly dive deeper. You mentioned the concept of the digital twin and digital shadow in your, specifically this came from you. And how is digital twin or digital shadow understood specifically in your exercises that you do?
Yeah, that's a great question. So when we started thinking about like how do you even implement a complex system like a 6-stage water treatment plant, the first step was not to like model every physical process itself, but to take readings from an actual operational water plant, which is the physical testbed that we built, and then input that into like a visualizer, like a virtual reality kind of a 3D visualization, which people can just understand and remotely observe and can operate remotely if they want to. So that's more of a digital shadow in which we take inputs from an operational system, and it's essentially just shadowing the actions of the physical system. Then Professor Aditya Mathur, who is in the audience here, he started work on implementing the digital twin, in which what happens when you want to provide your testbed or infrastructure to not just one team, one blue team, but 24 blue teams. You cannot provide one physical testbed to 24 blue teams to attack at the same time or defend it at the same time, because there will be conflicts, like there will be priority conflicts as well as many other operational issues with that. So for that, we need a digital version of the plant or the testbed, or a purely like replicable, purely extendable, virtualizable instance of the plant, which I can deploy not just on my own computer, but on the cloud for any educational institution to use, for any government to use, or for an exercise like Lock Shields, where 24 blue teams play together. So yeah, that's why it was important in the last couple of years to develop not just the shadow, but as well as like model those physical processes, like how does the formula for flow, which takes into account gravity and all these concepts from physics, apply to this digital world, and then also model the network traffic and accurately represent industrial protocols like OPC UA, which is used popularly, increasingly being used in all critical infrastructure. So how do we make it such that attackers or defenders cannot tell the difference between the actual operational real physical thing or the real cyber physical thing, which is the digital twin.
Right.
So yeah.
Right. Thank you. I'm going to take also the questions from the audience, if there is anyone. Yeah. Luke. Oh, I was pointing at you, but it's actually Luke.
So yeah.
Okay.
For sure. Sorry.
Go ahead, Gabor.
Okay, so this panel is recorded, and just to bite some click for us, I've been taking part in Lock Shields for 5 times, and as a green teamer, I have never defended any system, never attacked any system, and I always have the question how to defend a system against red teams. I do not know, but now I have a chance to ask how to defend your digital twin in Lock Shields against the red teams, because this is the aim, I think, that we have to serve. Thanks.
Yeah, firstly, that's an excellent question, because we always approach things with the mindset of an attacker, which is great. Like offensive security is how you find weaknesses or holes in any system. But the next step is how do you harden these systems? How do you plug these holes and essentially stop future attacks from happening? So most of the practices that people have learned in the cyberspace, which is information security, they still apply, because the points of entry of most of these attacks are still like cybersecurity strategies that attackers use. So these can be simple things like hardening your firewalls, understanding that there's no like ports open which shouldn't be open, and things like that. And then understanding, is there any operational or process-based weakness in the system? Like, is it possible that if I just overflow a tank in stage 1, it will have cascading consequences in stage 4? Now, this is something new which operational technology defenders have to learn. What is the process like? So when a blue team participant approaches an IT system, they have a very standard playbook in which they have like these 6 steps to follow. Is the firewall okay? Is the port working fine? Are the services configured correctly? And things like that. But when they approach an operational testbed, it's a different like bag of tricks for every operational system, or at least like different classes of tricks, because every fluid-based system is different. Like water, oil, all these systems, they have similar behavior because they are all liquids essentially. But when you are defending an electric grid or power system, you cannot be that relaxed with your defense strategy, because any attack happens in a millisecond, and you need to have different strategies to counter against that. So we are still in that phase in this a whole community in which we have to come up with like a better playbook for blue team systems. And there's already efforts in that direction. In red team, it's called the MITRE framework, in which that's a very, very easy to understand approach to approach red teaming. For blue teaming, we have to come up with something that can be like a theme for a future CyCon.
Right, thank you for the answer.
Yeah.
Luke.
Yeah, my question is about the physics of things. So we also include PLCs in our exercises. And I think it was 4 years ago we did the gas pipeline. And we ended up mimicking several sort of pipelines and valves and sensors, and the attack was against the PLC. And we ended up realizing that we have to essentially model the physics. So PV equals nRT and all this stuff, but even more complex. Because if we started to shut the valve here, how fast would the pressure drop over there, over 40 kilometers, say. Yeah. So all of this, and if you want to do the simulation correctly, then you got to model the physics.
Yeah.
And then you, in an exercise, you want to run a test run of it. You want to make sure the physics are good. So, but you don't want to wait 2 days for events to happen. So how do you deal with collectively building up the physical model of reality to allow the use of a digital twin in an exercise?
Firstly, that's an excellent question that is an extension of what BB asked me, like, why do we need a digital twin? We need it because we can't wait a day to replicate the actions that actually take a day. In a digital twin, you can essentially simulate an year of plant behavior in a day, or you can just speed the digital twin 100 times and just essentially see what actions take place in a plant throughout a day. So this can be modeled not just by physics, but also like chemistry. Like in our water system, we have pH sensors, conductivity sensors, and all the chemical processes which need to be modeled by chemical equations. So these physical systems are mostly dependent on time, and because we have the privilege to play with time in the digital space, which we do not in the physical space, digital twins become this very exciting area where we can essentially forecast what will happen if these initial conditions are configured, and I'm setting the twin to run at 100 times the speed. It's like watching a movie at 1.5x, 2x if you are short on time. So that really helps in not just reconnaissance after an attack takes place, but also forecasting what will happen in the future and predicting the consequences.
Yes, so this is very good, but what about the framework to do this? Are you aware? Because I mean, there's so much to be modeled. Is there some kind of standard? Was that your question? Yeah. This is what I do. Yeah. But is there a framework? Are there standards in here? Is there a plug and play where I can just come in with an equation or something and model some part of it?
Yeah, definitely. So Professor Aditya can describe that in a lot more detail. So you can meet him after the talk. But I'll give you the TLDR short version of that, which is that when we were building this testbed, we knew how the reactions and equations were modeled, because we had to build the physical thing as a whole. And all these programmable logic controllers, they take into account these equations when they have to decide on the logic. Like if the water is low, if the pump is off, if the valve is closed, these things have to happen. So when designing any such physical testbed, all these equations are considered. So it's the same equations which are then converted in a programmable logical form and represented that way. So the framework comes from systems design, which is used for constructing these testbeds as well. And it varies from plant to plant.
Right.
Yeah.
I will, as a moderator, I'll have to put an end to this. Unfortunately, this is a good discussion, but we have to honor the time and we have to move onwards. However, please do visit them at the iTrust booth and torture them more.
Page 347.
Exactly. Unfortunately. And now for something completely different. Still staying on the water theme, I welcome on stage Aybars. He is a PhD student and a research fellow at Norwegian University of Science and Technology. Oh, he has a very long experience working with even in the ship engine room and also on the shore. So please, the crowd is yours.
Thank you for the introduction, Bibi. Merhaba. Hello.
Thank you for joining us today. I will start my presentation immediately. I will talk about our papers published a couple of months ago by the Journal of Marine Science and Engineering. And I am not alone for this paper. We wrote this paper together with Associate Professor Vasiliki Kalos and also Professor Socrates Kassikas. The title of our paper is Towards a Cyber-Physical Range for the Integrated Navigation System. What is the purpose of this paper? We try to understand the requirements of a testbed for the integrated navigation system. What's the integrated navigation system? It is a system and combines the information receiving from different components such as AIS, GPS, ACDIS, and others to improve the safe navigation for conventional vessels. And it includes 6 tasks. These are detailedly described by the International Maritime Organization with some circulars. And the requirements for the collision avoidance and route monitoring is totally mandatory for an INS. Some of the requirements of the navigational control data and alert managements are mandatory again. And route planning and navigation site status and data display, these requirements for such tasks are optional. Our research consists of 2 parts. In the first part, we investigated the integrated navigation systems in different aspects, such as components, subcomponents, services, communication protocols, interfaces, dependencies and connections, data and data flow. We find a basement for this research because each manufacturer has different viewpoints. Some class requirements has different requirements. That's why we selected the IMO requirements because it is the god of the maritime. And to access the rules, current rules and regulations, we use the IMO Vega database offered by the International Maritime Organization and DNV. In the second part of our research, we look at the bridge testbeds in the literature in different dimensions, such as capabilities and functionalities, hardware components, monitoring and management tools, simulation and emulation tools, architectural models, research analysis, comparison of testbed, and potentiality for cybersecurity of a testbed. And we made a systematic literature review to reach out to relevant publications in the literature. And finally, we found 16 publications in the literature between the 2014 and 2020. Before the 2014, there were no publications regarding the bridge testbeds. And finally, we combined our extracted knowledge with the paper of Towards a Cyber-Physical Range for the Integrated Navigation System. However, in this presentation, you will take more than this paper. Firstly, we look at the components. However, International Maritime Organization doesn't have a component list for an INS because there are several factors, such as the size of the vessel as a volume or as a length, or navigation zone. That's why we look at the relevant circulars, relevant conventions, and we try to find the components as many as possible. And finally, we find 25 components developed for different purposes, such as positioning, such as to receive meteorological information or heading information. And then we look at the subcomponents. IMO defines only the performance criteria, actually. They don't interested in how it works, typically. And for example, ACDIS. ACDIS is an electronic chart, and we divide into 2 groups as a hardware and software. And hardware, monitor unit, processor unit, and control unit. Software, electronic chart, ACDIS software, and operating system. Of course, you can go deep, more deep. However, for us, it was adequate. And services. Service means functions, and we look at the IMO requirements again to define each component. For one of them is echosounder, is to measure and give the reliable information about the depth of the water under the keel, under the vessel, I mean. Communication protocols. Vessels are communicate with other vessels and shore through the different protocols, through the satellite, for example, or through some antennas. And another story is actually how the components communicate with each other. Interfaces. There is no any interface list for the in terms of the International Maritime Organization. That's why we look at the manufacturer brochures, and we found some interfaces such as Ethernet port or USB port or some ports for the serial communication. Dependencies. We reviewed all performance criteria, performance standards of the IMA for each component, and for example, for the radar, we found that it depends on gyro compass or transmitting heading device. AAS, EPFS is this electronic position fixing system. Actually, it is like GNSS system or aileron system. And speed and distance measuring equipment. And finally, we reach out that 7 components depends on different components. Produced data. Everybody knows that GPS give us a position information. However, for the International Maritime Organization, it is not adequate. According to the International Maritime Organization, GPS must provide also time information, speed information, speed over ground, or course information, course over ground. And finally, we made a model for an INS. And in this model, you can see different locations. For example, Monkey Island. It is the roof of the vessel, actually. Or the bridge is the center bridge and with wings. And what about the underkill? There are some transducers. Also, we try to show some communication protocols between the terrestrial system, between the satellite system. We would like to show the communication protocols between the vessels, vessel to vessel. And we would like to show the position of some components. For example, some antenna units or magnetic compass are in the Monkey Island, but some microphones is the starboard side, port side, bow side, and the aft side. Then we look at the bridge testbeds in the literature, and we found that 2 bridge testbeds are available in the literature. They are developing for performance tests of the components, to develop new technologies, and to make a risk assessment. And one of which is recognized by the IALA. I will mention about what it is. The testbeds are designed as a mobile or fixed. Real components or mimic sensor data can be used, and some tools for the monitoring or 3D creation, it is also possible. IALA. IALA is one of the most important maritime organizations in the world, and it is recognized by the International Maritime Organization. It is granted with consultative status. And EMIR Bridge Testbed, a maritime integrated reference platform developed by Oldenburg University in Germany, recognized by the IALA. However, it is not used for the cybersecurity studies. They have a fixed platform. It's a really large container with some antenna units. There is another container, but smaller one. However, it offers again the mobility. For example, in this photo, you can see that this container is on deck in service. Also, they can move their testbed with some aluminum bags. Another testbed is developed by the Hyundai. Hyundai used the real components on vessels in service. What is the drawbacks for our researchers to find a vessel? Because maritime sector is a conservative sector, and they are not open for the research or for collaborations. And however, for Hyundai, it was not difficult because they construct ships and also they operate ships. And also they develop some technologies. And for a technology developed by them, they use real vessels. And here you can see their schematic diagram, their test environment. As you can see, there are some real components on board ships, such as AIS, radar, GPS, and other real marine components. Of course, you can use also some simulations in your testbeds for different purposes. One of them is environment. What is environment? Firstly, you can need a geographical position, geographical map, and also you need weather conditions. You can create some sea conditions. You can make some scenarios with them. And traffic simulations. You need to create some. You need to put some vessels. Which kind of vessels? Tankers, containers, dry cargo vessels. Which one? And embody simulator. It is regarding the movement of the vessel. It is like through the starboard side, port side, or to bow side or aft side, like this. You can simulate the behavior of the vessel with embody simulator. And sensor simulations, of course. Sensor simulations means IAS simulation, GPS simulations, anemometer simulations, and others. You can create some virtual components. Of course, what is, for example, for the main propulsion system, bow thruster system, some steering system, what is the benefit of the virtual controls? You can carry it easier. Also, maybe you can use a test zone and you can occupy this zone with several components such as AIS system, some cameras, some weather sensors, and you can transmit the collected data through a router to your lab. We tested the bridge command. It's an open source software. Actually, it was first time used by the EMIR bridge testbed. And we found that it acts like a real ship network. Of course, it is too limited. However, it can be usable somehow. And also, you can combine it with some ship controller units as well. And another software we tested, NVA simulator. It actually broadcasts more ship network. However, visualization is limited or limited to compare to bridge command. OpenCPN is an electronic chart. It's used by the amateur seafarers and also some ship pilots. However, you can connect your real components, or you can use some NVA simulator or bridge command to this software, and you can take the NVA messages. You can collect the NVA messages. You can see the reaction of the simulators in the OpenCPN. Another one. During your research, during your study, you can need data sets, and one of them, of course, the AIS data set. And Norwegian Coastal Administration offers their AIS data free of charge through an IP address and port number. Use of bridge simulators, as I remember, the first time mentioned by the Plymouth University, some researchers in the Plymouth University, they also mentioned about the drawbacks and advantages. What is the drawbacks? For example, the maritime departments use the bridge simulators for training purposes. And if you damage their simulators, their trainings will be delayed. And also, these are costly equipments. It is really hard to touch the simulators in terms of, coding. However, it is a ready system, and that's why you don't need active software, for example, radar software. It is ready to use. Genoa University has a huge project, actually, and one of them regarding the cybersecurity studies. They're also planning to combine their full mission bridge simulator and cyber range. As I know, still an ongoing project. Taltech. Taltech also use a bridge simulator for their cybersecurity studies. And now they have another test environment. They are planning to make some research for the maritime cybersecurity studies. Maybe during the coffee time, they can give us more information about their testbeds as well. And NTNU, our university, Marine Department, purchased a simulator for the cybersecurity studies in particular, around 6 months ago. And we started to work on it. I would like to share our initial findings with you. Firstly, it is possible to connect with real bridge components, like AAS, GPS, real components you can combine. And we reviewed the network traffic, and it is compliant with the standards. The another one, we found in the front side 15 different kinds of components. However, when we look at the network traffic, it is less than seen. For example, heading information is provided by the gyro compass on a real ship. However, and in the front side we see the gyro compass. However, when we look at the network traffic, this data is produced by the GPS messages. We are trying to understand how we can create a remote connection opportunity. This is one of the problems, because the Marine Department is different city in the different than us, and maybe a remote connection could be also better for us, maybe also better for our stakeholders. The another one is potential scenarios. How can we create some scenarios using a simulator? This is our next question, actually. And we are trying to understand the combination of the simulator with some tools, some cybersecurity tools, or some data sets. How can we combine them? This is our next question. Thank you for listening to me. If you have any questions, maybe, okay, then maybe you can ask during the coffee.
Right. Before I open the floor to the questions, so thank you. Take the seat. As okay, maybe here you don't need a warm-up, but every big rock band needs a warm-up question. So there you go. I'll start with the question that I have prepared. I have multiple questions for every one of you. So
thank you so much, Evie.
So you are looking at the concept of the simulators who are designed primarily to train the crew on the operating the vessel, and now trying to look how those simulators can be adjusted to train cybersecurity of the vessel, right? At least that's what in the nutshell what I understood. And you say nodding, so it means okay. So I understood
it's okay,
right.
No problem. Continue.
The first question I have: how close those replicas are to the actual systems, and if there are already test beds and the individual components exist, why would you need to struggle and create test bed with a full equipment?
Yeah. Firstly, with the full equipment, you can create different scenarios. I would like to explain one scenario if possible. For example, GPS spoofing. It is one of the well-known attacks, or one of the well-known vulnerabilities for the GPS. GPS is connected to the ACTIS electronic map and connected to track control system. For instance, during the GPS spoofing attack, track control system, what is that? It is called like autopilot, actually. If you, in case of a GPS spoofing attack, it is possible, theoretical, this is my idea only, misdirect the vessel, because track control system depends on the ACTIS. ACTIS depends on the GPS. And the starting initial point is the GPS, and for this reason, I think it is possible to misdirect the vessel. You can, if you have a full system, if you have more components, you can create more scenarios. This is the one issue. Another one, if you have a system, yes, this testbed for the cybersecurity. But if you have a system, you can also make some research for the operational side. For example, for the awareness of the seafarers. Because at the end of the day, for the conventional vessel at least, we need seafarers. And today, many people mention about that. The weakest point is the seafarers. It is open to discussion, because also the strongest point from my point of view, because at the sea, we need these seafarers. Yes, is adequate for your...
Right, perfect. We'll take the question from the audience. Please, go ahead.
Renike. Okay, I will actually stand up now. Thanks, you all, for your presentation. Super interesting. So for me, coming from the cyber threat intelligence sector, one question is really emerging here. So you all are gathering quite a lot of data. And especially if you look at the maritime sector and if you look at GPS and AIS.
Regarding the messages, you mean? NMA message protocol you talk?
One second. For example, Sid was talking about that they had gathered over a terabyte of data in their exercises. You're speaking about all the tools you're working with for monitoring the AIS, the GPS, and so on. And I just quickly looked it up again. The AIS spoofing is not a new thing, right? So this happened in 2017 to at least, I think, 20 NATO vessels. So it has happened, and it has happened in the alliance. So from a CTI standpoint of view, could you give some examples to which tools you use to analyze these massive amounts of data and to find like some real-time and actionable threat intelligence on the cyber vulnerability? So which CVEs have been exploited? How can you react up on that? How can you immediately patch and update and all of that?
Actually, we didn't do that. However, another project, it was done. As I remember, for example, Secure AAS. AAS data actually includes 4 types of messages: synthetic messages, dynamic messages, voice-related messages, and safety messages. And real time, they collect this kind of data and compare it. For example, if they started to get some data from the AAS regarding the ship type. However, the cargo is different than ship type, is not compliant with the ship type. It gives an alarm. We didn't do, but it was done in another project. They compared the AAS data with another AAS data. This is an option. Actually, we published a papers with Ahmet. He is my office friend and also my close friend. We checked the NMA messages. You know NMA messages. And we try to establish the NMA messages, different fields, I mean. NMA messages, maybe some people doesn't know, NMA messages consist of several fields. And we compare this field with another messages in our papers. For example, if a message regarding the RPM, revolution per minute, running, I mean, there is a data for the RPM. For example, 60 RPM. Instead of these messages, there is no any movement of the vessel. We can understand that there is an anomaly. This anomaly could be relevant with the cyber attack or maybe sensor failure.
All right. Yeah, I will, Gabor, have you been introduced? Does anyone know that you are a PhD student and you are also doing research in naval systems? Gabor, my friend, you have a question.
Yeah, this is why this panel is here, because they are supporting my PhD. Estonia is a very open-minded country, and if I tell my boss that I do not know the answer, they usually accept this answer. The last question was that, is it possible to integrate maritime components to our cyber exercise log shields? So I transferred the question to you guys, either as a digital twin, either as a virtualized test bed. Would it be possible?
Aybars, for sure. That corresponds also with the questions that I have.
Could you tell me again your question, please?
Yeah, I will try.
I can repeat it.
How could we integrate virtual ship or digital twin of a ship to our exercise? Do you think that it is feasible, possible? Will you do it for us?
I think it is possible, and today it is trying to trying to succeed some researchers to do that. And of course, there are some difficulties, I know, because manufacturers also use the different viewpoints, different protocols. There are some difficulties, and there are some, I remember some projects I don't want to mention here, but it was unsuccessful. However, if also the manufacturer maybe could be open for the discussion, it could be possible, I think. This is my viewpoint.
All right.
But there's an unsuccessful project.
We may learn.
Sorry for that.
We may learn from the unsuccessful project. The best things that we learn is from our own mistakes, even though someone told you not to do so. With this, I would like to also wrap up quickly the panel. So, digital twin is something we understood is an ambiguous term. We see that Joe, my friend here, is trying to replicate a naval dockyard and bringing it as a model, as a virtual model. Sid is using a digital shadow technology where it's interlinked already with a physical system with the one in the virtual space to speed up as you would quickly watch a movie or listen to an audiobook, which is a really awesome approach. And Aybars, you're taking already a miniature version of hardware that is representing a huge vessel, right? And you're trying to play around with it. So there are different approaches that we can take on this. I would like to thank each one of you, and specifically you as the audience, for being awake and asking questions, really engaging questions. So a round of applause for everyone. Thank you.